Hi ladies and gentlemen, the topic of FYP that I will present is numerical simulation of Retrofitted Multicyclones Separator RMC and scale-up design based on computational fluid dynamics CFD. This is the overview of the presentation, which consists of introduction, problem statement, objectives, methodology, results, and conclusion. In this study, it's important to know what is particulate matter. Basically, particulate matter can be divided into PM1 ultrafine particle, PM2.5 fine particle, PM10 coarse particle. It's undeniable that particulate matter can cause serious environmental problems and health problems. Cyclone separator is chosen as air pollution device in industry due to its simple design, low capital and maintenance costs, and able to withstand high temperature and pressure. I believe that most people heard about single cyclone separator and multi-cyclone separator, but do you know what is retrofitted multi-cyclone separator RMC? Retrofitted multi-cyclone separator is the latest modified conventional multi-cyclone separator with the additional suction stream at the dust hopper. It has axial inlet and 4 small identical cyclones. This is the problem statement of this study. If the cyclone velocity is too high, it will lead to high pressure drop and high cost. If it is too low, it's very difficult for particles to reach the dust collector. And also, if the suction velocity is too high, it's very energy consuming. And if it is too low, fine particles are hardly to be attracted. Hence, it's very important to determine an optimum velocity in order to have a higher efficiency RMC. There are total 4 objectives in my study. The first objective is to study the flow field of RMC under the influence of various cyclone and suction velocity. The next objective is to predict the performance of RMC under various cyclone and suction velocity. And the third objective is to understand the phenomena and particulate movement in all conditions. The last objective is to scale up the retrofitted multicyclones into a larger scale compared to the original RMC. This is the scope for Objective 1, which are studying and understanding the internal flow field of original retrofitted multicyclone, and at the same time, study and implementing CFD on original RMC. This is the continuation work where the cyclone velocity and the suction velocity are extrapolated from the previous work. This is the scope for Objective 2, where the performance of RMC are related to the separation efficiency and also the pressure drop, whereas the operating variables are cyclone velocity, suction velocity, and also particle diameter. This is the scope for Objective 3 and 4. In the scope of Objective 3, pressure control and velocity control of gas are visualized through the application of CFD. The red color region represents the gas move with highest pressure or highest velocity. Interestingly, not only gas flow pattern, particulate movement also can be observed through CFD. Whereas in the scope of Objective 4 is to withdraw and scale up to 9 small identical cyclones. This is the summarized process flow of methodology. In the stage 1, the 3D drawing of original RMC was constructed in the SolidWorks. In the next stage, which is for validation purpose, the simulated results of pressure drop then compared with previous experimental value of pressure drop to prove that the CFD has great accuracy. In the stage 3, separation efficiency and pressure drop of original RMC were predicted using CFD simulation by setting the extrapolated velocities. In the stage 4, pressure control, velocity control, and particulate movement were visualized through the application of CFD, while for last stage, we draw in SolidWorks and scaling up from 4 cyclones to 9 cyclones. After that, run the CFD simulation of scale up RMC and move back to stage 4, which is visualization of the results. Cyclone geometry is the primary step to be done in SolidWorks before exported to CFD. Cyclone geometry is important as different cyclone geometry might affect the internal flow field of air and movement of air solid. This is the geometry of original RMC with 4 small identical cyclones. This is the geometry of scaled-up RMC with 9 small identical cyclones. Both of them have sample inlet, clean air outlet, and also suction outlet. Basically, CFD is divided into pre-processing, solving and processing, and post-processing. In the pre-processing, it consists of matching of RMC and scale-up RMC, initial conditions, setting of computational method, RMG K epsilon turbulence model, and also boundary conditions. While for solving and processing, it involves computational calculations, iterations, and convergence. Whereas in post-processing, it includes the result analysis and the visualization of the results. Matching is a process to solve the equations iteratively using finite elements. Different match can affect the simulation's precision, convergence, and pace. For example, finite match will produce accurate result but time-consuming. Hence, appropriate match is important. This is surface matching of original RMC. This is surface matching of scale-up RMC. This is the CFD setting of boundary condition in original RMC, where the cyclone effective inlet velocity of 5 m per second and 60 m per second has been extrapolated from the previous study. This is the CFD setting of boundary condition in scale-up RMC, where the cyclone effective inlet velocity is 40 m per second. Same sample injection being used as in the original RMC, which is PONFA with density 1071 kg per meter cube. Then move to stage 2, which is the validation of CFD against experimental data. Validation is a process of determining how closely the computational findings match the experimental data. As shown in this table, the percentage difference of inlet static pressure and the percentage difference of outlet static pressure are less than 10%. This indicates that the CFD has good accuracy of the results, thereby can be used to obtain more data that is the limitation in the experiment, such as pressure control, velocity control, and particulate movement. The result of separation efficiency of original RMC that obtained from the CFD have been summarized in this table. The inlet stream represents the total particle trapped, while the cyclone stack represents the total particle escape, and the suction stream represents the total particle that being extracted out, and dust hopper represents the total particle collected. This is the formula of separation efficiency. Separation efficiency in RMC equal to inlet stream minus cyclone stack over inlet stream times 100%. Generally, based on graph 1 and graph 2, the PM10 possesses the greatest separation efficiency as compared to PM1 and PM2.5. Moreover, increasing cyclone effective inlet velocity also contributing to greater separation efficiency of particles as shown in graph 1 and graph 2. Interestingly, by comparing graph 1 and graph 2, the graph with suction 20% illustrated better separation efficiency than the graph with suction 10%. This is stage 4, which is visualization of pressure control of gas in the original RMC. Position A represents inlet stream, while position B represents outlet stream, and position C represents dust hopper. As can be observed from this table, higher cyclone velocity can increase negativity of pressure, and also higher suction percentage able to create a vacuum state in the dust hopper with more negativity of pressure. This is the velocity control of gas in the original RMC. Position A represents inlet stream, position B represents suction outlet, position C represents inlet vortex, position D represents vortex. As can be observed from this table, higher cyclone velocity can increase the velocity of gas at all positions, and also higher suction percentage can create high pressure difference that pull the vortex further down into the dust hopper and increase the velocity of gas at all positions. This is the particulate movement by side in RMC at 5 m per second with suction 10% and 20%. As can be observed from this table, the inlet velocity of particle increase with increasing particle size. This is because heavier particles possess greater inertia that tend to move in a straight line with uniform velocity. However, the vortex velocity of particles decrease with increasing particle size. This is because greater effect of wall friction exerted on larger particles that will slow down the swirling flow velocity of particles. Obviously, there is lesser particle escape for PM10. This is the particle movement by side in RMC at 6.2 m per second with suction 10% and 20%. With cyclone velocity of 6.2 m per second, it shows lesser particle escape as compared to cyclone velocity of 5 m per second. As can be observed from this figure, the particle movement by size in RMC at 60 m per second with suction 10% and 20% shows similar trend as previous particle movement at 5 m per second and 6.2 m per second. This is the particle movement at dust hopper and suction stream at 5 m per second with suction 10% and 20%. Position A represents suction outlet and position B represents dust hopper. As can be observed from this table, suction particulate velocity increases with increasing particle size, and also higher suction percentage contribute to greater particulate velocity at suction in respect to particle size. This is the particular movement at dust hopper and suction stream at 6.2 meter per second with suction 10% and 20%. As can be observed from this table, at cyclone velocity of 6.2 meter per second, it has greater particulate velocity at suction outlet and dust hopper as compared to cyclone velocity of 5 meter per second. This is the particular movement at dust hopper and suction stream at 16 meter per second with suction 10% and 20%. As can be observed from this table, with cyclone velocity of 16 meter per second, it has greatest particulate velocity at suction outlet and dust hopper as compared to cyclone velocity of 5 meter per second and 6.2 meter per second. This is the pressure contour and velocity contour of gas in scale RMC with suction 10% and 20%. This is the particular movement by size in scale RMC as can be observed from this table. It shows similar trend as original RMC. And it also shows lesser particle escape as compared to original RMC, and hence it has better separation efficiency. Based on the comparison graph of separation efficiency between original RMC and scale RMC, the scale RMC shows better separation efficiency as compared to the original RMC, irrespective to the particle size. In conclusion, all the objectives are said to be achieved. For objective 1, it can be concluded that through the visualization of this contour, higher cyclone velocity can increase the flow velocity of gas at all positions in RMC, and higher suction percentage also can increase the flow velocity of gas toward dust hopper. For objective 2, it can be concluded that higher cyclone velocity contribute to better separation efficiency, and higher suction percentage enhance more on the separation efficiency. For objective 3, it can be concluded that PM10 has the best separation efficiency as compared to PM1 and PM2.5, as lesser particle escape has been observed from the particular movement. For objective 4, it can be concluded that scale up RMC shows the similar trends of flow field as in original RMC, and scale up RMC has better separation efficiency than original RMC due to larger diameter of suction stream that has larger cross-section area. Thanks for watching.